Hey everyone, hopefully this is just one last video lecture for you. I'll be accompanying today's video lecture with a live Zoom session where I will answer all the questions that you put on the survey for this week and also any questions that you have live for me. So if there's anything from the past week of video lectures you're confused about, if you want to see more examples of a particular topic, if there's homework questions you're stuck on, bring those questions to our live session and I'll answer as many as I can. So, since we're doing that for roughly half the class, this is meant to be a half class lecture, so it should be a little bit shorter than the others. But last time we talked about computing some limits when you had an indeterminate form, particularly if you had a fraction and both the numerator and denominator are getting small or approaching zero, or if both the numerator and denominator are getting large, either positive or negative, approaching infinity. These are called indeterminate forms. Because it really sort of depends on exactly how quickly the numerator and denominator are approaching zero or infinity to determine sort of which one is growing faster and which one is going to dominate and what the result is going to be. But if these are mixed and matched, we do not have indeterminate forms. So if you have a fraction where the numerator is growing toward infinity, but the denominator is shrinking toward zero, or vice versa, these are not indeterminate forms. If we just sort of think about what's going on here. So, if you've got a numerator that's getting big and a denominator that's getting small, both of those are working together to result in a very large number. Right? If you take a large number and you divide it by a small number, well, dividing by a very small number is the same as multiplying by a very big number. So you're just doing big times big and it gets even bigger. So if you've got a fraction where the numerator is growing and the denominator is shrinking, overall that value is growing to either positive or negative infinity, and you have to sort of think about the sign, whether your numbers that you're getting out are positive or negative to determine which one. And on the flip side, if you've got a numerator that's tending to zero and a denominator that's tending to infinity, then overall these values will be approaching zero. Right? Because if you divide by a larger and larger number, that's going to make your overall number smaller and smaller. So there are some cases where you get something like this. Like for example, let's say we wanted the limit as x approaches 4 of x plus 2 over x squared minus 8x plus 16. All right, so if we try to plug in 4, if we try to do the substitution method, we get 6 over 0. So our numerator, as x gets closer to 4, is getting closer to 6, and our denominator is approaching 0. And so we're taking a number close to 6 and dividing it by a smaller and smaller and smaller number, which is the same as multiplying it by a bigger and bigger and bigger number. So what's happening to the values of this function is that they're growing and they're approaching infinity. And on the graph, what that's going to look like is a vertical asymptote. Now we sort of have some options for what a vertical asymptote can look like without doing any analysis of the function itself. You know, if at x equals 4 we have a vertical asymptote, either the function is approaching infinity from both the left and the right, or the function is approaching negative infinity from both the left and the right, or it's going up on one side and down on the other. Now, if we're in this case here, then the limit will be positive infinity. If we're in this case, the limit will be negative infinity. And if we're in this case, the limit doesn't exist because the limit from one side is positive infinity and the limit from the other side is negative infinity. So let's try to figure out which of these situations we are in. And the way to do that is to sort of plug in values on either side of the asymptote to figure out if your results are positive or negative. So what I typically like to do is I like to make a little number line and mark all the places where the function can change signs. So at x equals 4, it could switch signs because of the asymptote. And also at x equals -2, it could switch signs because the numerator is 0. And so the function is equal to 0 at -2. So on one side of that, it could be positive. On the other side of that, it could be negative. And then I just pick a value from each interval and plug it into the function. So since I want to figure out what's happening on either side of 4, I'm going to plug in x equals 3 and x equals 5. Now when I plug in 3, I get 5 divided by 1, which is a positive number, which is really all I care about. And if I plug in 5, I'm going to get 7 over 25 minus 40 plus 16 is also 1. So I see that my function values are positive on either side of 4. So that means we're in a situation where the graph is going to look like this near our asymptote. And so our limit is equal to positive infinity. Next, I want to do a couple of examples from trig. First one, like the last example, involving asymptotes, and then one that's completely different. But let's say we want to know the limit as x approaches pi over 2 of the tangent of x. Now, the tangent of x, remember, is sine over cosine. And the problem is if we try to plug in pi over 2, the sine of pi over 2, if we think of our 90-degree right angle here, it crosses our unit circle at the point 0, 1. So the sine is equal to 1 and the cosine is equal to 0. And so the tangent of pi over 2 is actually undefined. Now, we just want the limit as x approaches pi over 2. Now, if we choose an angle slightly less than pi over 2, we'll get, x and y values for that point that are positive. And so everywhere on this quadrant, the tangent is positive. But if we picked an angle slightly bigger than pi over 2, here x is negative and y is positive. And in this quadrant, the tangent function then will be negative. So we're in a situation where if we approach pi over 2 from the left, if we choose an angle slightly smaller than pi over 2 but approaching pi over 2, our values are going to be positive and growing. And if we approach pi over 2 from the right, from the other way, our tangent values are going to be negative, but also, growing in magnitude. And so overall, this limit does not exist. And if you were to graph the tangent function, what it looks like, I'll put pi here, I'll put pi over 2 here, is that it has a vertical asymptote at pi over 2. And the tangent of 0 is 0. Tangent of pi over 4 is 1. And you get sort of an asymptote that comes up like this. You also have an asymptote at negative pi over 2 and at 3 pi over 2 and 5 pi over 2 and all the pi over 2s. And you end up getting a shape that repeats kind of like this everywhere on the graph. So if we are sort of zeroing in on and looking at what's happening to the function near pi over 2, well, it's a very different picture if you're a little bit less than pi over 2, in which case your values are growing toward positive infinity, versus if you're very close to pi over 2 but slightly greater than pi over 2, the values of the function are descending down toward negative infinity. So overall, this limit does not exist. Now earlier we saw, using some sort of numerical approximations, that the limit as x approaches 0 of sine of x over x is 1. So now we're going to use a theorem called the squeeze theorem to prove that this is actually true, rather than just sort of guessing it based on a numerical estimate. So here's the idea. Suppose we want to know some limit as x approaches c of some function. And we sort of know a function that's always less than this function and a function that's always greater than this function. So I'm going to name those functions L for lower bound and U for upper bound. So let's say we know a function L that's always less than or equal to f of x. And we know a function U that's always greater than or equal to f of x, at least for all x values near c. And let's suppose further that we know the limit as x approaches c for L of x, and it's equal to, say, capital L for limit. And let's say that's also equal to the limit as x approaches c of u of x. Then we can conclude that as x approaches c, f of x also approaches L. So this is what's called the squeeze theorem. And it's best to sort of understand what's going on with a picture. So let's say we have a graph. We have some point C. And we have some function u up here. And we have some function L here. And f, we don't exactly know what's going on with f, except we know that it's like always in between here. Well, then if u and L both have the same limits at this particular point C, then since f is sort of squeezed between them, there's nowhere else for f to go. So the limit for f must also be equal to L. That's the idea. So here's an example of how we can use this theorem. Let's say we want to know the limit as x approaches 0 of x times the sine of 1 over x. Now this is a little bit confusing because, well, certainly this factor is going to 0, but 1 over x, as x goes to 0, 1 over x is going to infinity, and the sine graph just kind of waves back and forth. So this doesn't really have a clear limit. So we can't just evaluate this by substitution. But one useful fact about the sine and cosine functions is that they always live between -1 and 1. So no matter what you plug into a sine function or a cosine function, the output is always between -1 and 1. And so I'm going to multiply all of this through by x, but I'm going to do absolute value of x because I want to multiply by a positive number. Alright, so my function here then is always less than or equal to the absolute value of x, which is like x times 1. And is always greater than or equal to negative that. And the limit as x approaches 0 of the absolute value of x is 0. The limit as x approaches 0 of negative absolute value of x is also 0. And so the function stuck in between must be 0 as well. Now what the picture looks like here, this is my upper bound function, the absolute value function. That's like a V shape. Here's my lower bound function, negative that, so the same thing but upside down. And this x times sine 1 over x is like a crazy wave that gets bigger as you go out. But it always lives in between this red line and this blue line. And so at 0, the limit must be, at 0 this function is undefined because of the x in the denominator there. But as we get closer and closer to 0, the values of this function must be getting closer and closer to 0 as well, just because it's stuck with the red line above it and the blue line below it, and those lines are converging to 0 at that point. Okay, so I think I'm not going to prove the limit of sine of x over x is equal to 1 in a video lecture because it's a little bit technically complicated, and I think it's better to do in person when you can ask questions. So the topics that I plan to talk about together in class on Wednesday include limits at infinity. So that's thinking about sort of what happens as x approaches positive or negative infinity for a function. Basically, it's asking about the end behavior of the function. What does the graph of the function look like on the extreme left and right edges of the graph? As x gets bigger and bigger and bigger in either direction, what's happening to our function? So we'll learn some rules and tricks for figuring out what that looks like for all the functions we care about, polynomials, rational functions, etc. And then we'll learn the intermediate value theorem. Which gives us a way when we have continuous functions to sort of approximate roots of the function. So that's sort of what's up next. But the plan will be to talk about both of those in class together on Wednesday, since I want to keep this relatively brief. So I hope to see you at our live Q&A on Zoom tomorrow or this afternoon, I guess, depending on when you're watching this. I'll be doing that from 12:30 until 1 o'clock. And then hopefully I'll actually be able to be back on campus with you on Wednesday. So have a great day, and I'll see you soon.